Hi. Hello everybody, I am indeed Tim Parker, and this is my presentation on formalizing ethics in logic. So, I will be talking about how values written in formal logic can be used in the design of ethical and safe agents. I will cover some of the good reasons to use logic, but also some of the challenges that exist that need to be overcome. In particular, dealing with moral dilemmas, which is any scenario where two or more of your values clash, you can't satisfy all of them, or in cases of non-determinism, where the satisfaction of some values cannot be guaranteed. And this presentation is based on the work done in my PhD thesis thus far, so is the work of myself and my two supervisors, Umberto Grandi and Emiliano Lurini. So why use logic? So one of the main features of logic, particularly I think that's relevant in a sort of AI safety context, is that it's comparatively easy to provide formal guarantees for a logic-based system, certainly compared to a neural network or other machine learning-based system. Logics can also be incredibly rich in terms of the properties that you can use them to talk about. You can express temporal properties, you can talk about beliefs and desires of agents, you can talk about capabilities of agents, so things that agents are able to guarantee or able to do. And also you can use logic or a logic-based system as merely a part of an overall system that in principle at least can guarantee the nice properties of logic, the verifiability, without necessarily compromising on that system's decision-making power. So here's a very basic example. You have the environment that inputs information into some kind of decision maker that can be any kind, you know, neural network, some complete black box. That then outputs its decision. The decision is then passed into some sort of logic-based verifier that checks if the intended plan or strategy or action meets certain values that we think are important. If it does, then the action gets output, goes on to affect the environment, and if it doesn't, it says no, try again. So obviously this is quite a sort of heavily simplified system, but I think in principle this could be quite a good idea. So the model, this is the model, just the logical model that I've been doing most of my work on. You have a set of just logical propositions that describe the world. You have a set of agents and a set of actions for those agents. We have an action theory which describes how the world changes in response to the actions of the agents. And we have a start state, which is just where you start from. Given then, so either plans or strategies, a plan is just a sequence of actions. It's a function from time to actions, and a strategy is a function from histories to actions, meaning that strategies can actually vary depending on what's happened so far, making them much more flexible. If you apply those to all agents and then apply that to a start state, you will get a history, which is just a list of all the actions that the agents have performed and how the states changed in response. And we then analyze the values over the history. So a value either satisfies some value or it does not. Obviously also various ways to expand this, make it more complicated, more realistic. Okay, so some of the problems. So I'll give a couple of honorable mentions, which are problems or challenges with this model, which I think are very important, but which I haven't really been able to study in depth. One, which I think we had a presentation on yesterday about problem of value selection. So there is a lot to be debated about how we select our values, who should be involved in selecting our values, how many we want. So I tend to assume in my work, I make the very optimistic assumption that we just have arrived at a set of values that we all agree on that are very good, and we've also decided on the relative importance of all of these values. And so to try and keep the work as general and accessible as possible, I make sure that the system can handle a very wide variety of different value types. So, there we go. Because we evaluate values over histories, and we just say temporal properties of histories, the model is quite a natural fit for consequentialist type values that just say, well, the value is satisfied if this particular state of affairs is achieved. But because we can also talk about actions that are performed by particular agents, we can also express more deontological values. of the form, this particular type of action is forbidden in this particular context. Another thing, ensuring model accuracy. So again, logical formulas I think are great. They're very easy to evaluate, but they have to be evaluated over a logical model. You can't just evaluate a formula over the real world. That means you need some sort of system that takes in data from the real world and transforms that into a logical model. And depending on exactly what sort of propositions you want to be contained within this model, that can be very difficult to do. So here's some examples. We have this car. We suppose it's got some sort of autonomous capabilities, and we think about what are some of the values this car might want to have. So the first one says, at all points in time, if the driver is drunk, then make sure that the autonomous driving mode is fully engaged. So never let a drunk person drive a car. Now, presumably this is a good value, and this proposition is very easy to evaluate. We can assume the car knows if it's in autonomous driving mode or not. This proposition is much harder to evaluate, particularly if you don't want the car to be sort of repeatedly taking blood samples of the driver every time the driver gets in. Another similar one, if the roads are icy, drive slowly. You know, this could be formalized in a more complex way, such as always drive below 20 kilometers an hour, or never exceed a certain amount of lateral g-forces. So again, this one we can say probably quite easy to evaluate, but then whether the road's icy, maybe that's a bit harder. You might want some sort of combination of temperature sensors and camera data, and even then might not be perfectly reliable. And then a final sort of very general one, we could just say, well, just make sure that the driver is never harmed, or that no human or animal in the vicinity is harmed. Again, a further complex problem here is even defining what is harm. Because from a legal and philosophical perspective, exactly what is and isn't harm is quite a contentious thing to define, particularly in some of the edge cases. Okay, so one of the problems I have actually studied is the issue of a dilemma. So a dilemma occurs when it is not possible to satisfy all of an agent's values at the same time. So I'm guessing a lot of you will be familiar with this particular, probably the most famous philosophical, theoretical moral dilemma. The trolley problem, you have a lever, you push the lever one way, the trolley will go this way and kill one person, the lever goes the other way, the trolley will go this way and kill 5 people. And usually you set it up as some sort of dilemma that says, well, if we leave the lever alone, then it kills these people, and if we push the lever, it kills this person. So we have a conflict between the value that says, minimize the number of people that die, which is a good value, and the value that says, don't directly take actions that cause people to die, which is also a good value. So the proposal for solving dilemmas like this, or in general, is we simply have a lexicographically ordered value base. So again, we're assuming that we have a priority ordering over all these values, and then we just order them by priority and say, well, we assume that the values in the first set are just sort of infinitely more important than all the values below them. So we just compare any plans or strategies according to the first value set, and then if we can't decide because they're equally good, you look at the second, and then so on until the last one. 2 ways of doing this comparison. The first is quantitative. You just count the number of satisfied values. This is very simple. The second is qualitative, which is a bit more complicated. So here we say that we only prefer one set of values if it is a strict superset of the other set. So here we can say, well, this set is clearly better because it satisfies all the values of this set plus this extra one. But in this case, well, it's not really clear which of these 2 sets are better, because this one satisfies more values, but this one satisfies this extra value 4, and maybe value 4 is actually really important. So this very often results in cases of non-decision like this one. And I would argue that in some cases that's actually a good thing. Because we might have a system, an autonomous system that's quite smart, so we want to use it to make decisions, to save effort on humans. But we don't trust it to make difficult moral decisions. We only want it to make the easy moral decisions. And I think any decision that satisfies this criteria is an easy moral decision. Because you're saying, well, we have 2 options, and one of the options is just very, very straightforwardly better than the other. So we trust the AI, this autonomous agent, to make a decision in this case. But in this case, well, maybe we don't trust it, because these values, while they might all be values that we like, the relative weighting of those values could be something that's quite subtle and quite context dependent. So if this occurs, then it should call on some higher level system, which may be a human operator or may just be some much more advanced but slower reasoning engine. Okay, and another issue is the idea of causal responsibility, which is the case, well, it's relevant in cases where satisfaction of a value cannot be guaranteed. And you say, well, if you can't guarantee the value, you should at least try to minimize your causal responsibility for the violation of that value. And so in the most general term, causal responsibility says that the agent is part of a minimal coalition whose strategies are jointly sufficient to guarantee the outcome. And what does that mean? So consider this example, where a family of 4 has decided to push their car into a river. I don't know why. Possibly it kept taking blood samples from them to see if they were drunk. So the car's quite heavy, so we can suppose it takes 3 members of this family to push the car into the river. But because they're all so angry, all 4 of them decide to push the car into the river. So in this case, the minimal coalitions is any coalition that contains exactly 3 family members. Because the coalition of 4 is not minimal, because you can take away any member and the coalition is still sufficient. Any coalition of 2 or less is not sufficient, because they wouldn't have been strong enough to push the car by themselves. So we have 4 coalitions of 3 agents. And because then every agent is in at least one of those coalitions, we can say every agent is causally responsible for pushing the car in the river. Certain relevant subtypes of that, if an agent is in a minimal coalition of just themselves, we say they are actively responsible, so they personally caused the thing to happen. So suppose Pink over here is actually really strong and can push the car all by herself. Then even if the other agents joined in, we can say Pink is kind of very strongly responsible, Pink is actively responsible. Another notion is passive responsibility, where I is in all minimal coalitions. So in this case, suppose only these 3 push, and we downgrade Pink again. Then we can say all of these 3 agents are passively responsible because there's only one minimal coalition and they're all in it. And passive responsibility means that you, by acting differently, could have prevented the outcome. Whereas in the version where they all push, they can all theoretically try and give some excuse for not being responsible by saying, well, look, yes, I contributed, but even if I'd acted differently, the outcome would have still occurred. But with passive responsibility, that's not true. So you have some alternative way, equivalent way of evaluating these responsibilities. So active, you say, given the plan of the one agent, in all cases where that plan occurred, we get this outcome. And there's some outcome where it doesn't occur, so I'm not responsible for the sun rising in the morning because that was always going to happen. And passive responsibility says the thing happened, and if we fix the actions of the other agents and change your actions, it's possible to have the thing not happen. So in a meaningful sense, I could have stopped it. Okay, here's a big wall of text. Okay, so classification of strategies. This is some newer work, just looking into strategies, which is the more complex version of plans. Some properties of strategies that are fairly well studied. You can say winning strategies that just guarantee the outcome regardless of how the other agents act. Dominant strategies, a bit more complicated. Basically, it wins whenever winning is possible. So if the other agents don't play a winning strategy for the negation, then your strategy is winning. And best effort means you just satisfy the formula against a maximal set of strategies from the other agents. And then it turns out there's some quite nice equivalence results between the notions of responsibility that I've just covered and these notions of strategy classification. So winning pretty much exactly corresponds to active responsibility. Problem, of course, winning strategies are not guaranteed to exist. Dominant strategies always avoid causal responsibility. So passive, active, causal responsibility in general. But again, dominant strategies don't always exist. And then best effort strategies are kind of the nicest because they are guaranteed to exist, and they have 2 other very nice properties, which is that if winning strategy exists, all best effort strategies are winning. And if a dominant strategy exists, all best effort strategies are dominant. And so in principle, you can verify that an agent will always select a best effort strategy, because we know that a best effort strategy will always exist, And by always selecting a best effort strategy, we can guarantee more or less that the agent will always minimize its causal contribution to the violation of any values. Okay, another use of responsibility is that in some cases, you might actually wish to avoid responsibility in both directions for some formula. Particularly if you think that phi and not phi are probably both quite important, but we don't necessarily know which is better. So for this example, we have this. This is an autonomous house, and it has some participants or some inhabitants. Maybe they're outside at the moment. And now it's quite important that the inhabitants of the house are free to go outside if they want to, but also are free to stay inside if they want to. So you say that the house should neither be actively responsible for them having to stay outside, but also should not be actively responsible for them having to stay inside. It should take a strategy that lets the inhabitants free to decide what they want to do. So this, at least in some way, goes towards the idea of creating a sort of minimally disruptive strategy. So a strategy that achieves the goals the house has, such as, maintaining a constant temperature or something like this, but otherwise is minimally disruptive to the world. And you can, in fact, directly formalize this in logic using this particular notion called STIT, which is seeing to it that. And this would look something like this. So we say it is not the case that the agent I, which is the house, guarantees that, STIT, at some point in time, all the inhabitants are outside. And it is also not the case that the agent guarantees that at some point in time, none of the agents are outside, none of the inhabitants. So the house must pick a strategy such that neither of these outcomes is guaranteed. Okay, so in conclusion, I have outlined how logic can be used to guarantee safe and ethical behavior in artificial agents. I have prevented some of the challenges that such an approach faces, moral accuracy, and then in particular moral dilemmas and minimizing causal responsibility and potential solutions to some of those problems. And future work, thing currently being worked on, how to combine these notions of responsibility anticipation, which is minimizing the responsibility for a plan that has not yet been executed, and then the notion of multiple values and moral dilemmas. Because I can do responsibility for single values at a time, I can do dilemmas with multiple values. I haven't yet got a good way of combining these two. Thank you for your attention, and any questions?
All right. Any questions from the floor? Good. Yes, at the back in the middle. Please keep your hand raised.
Thanks, that was very interesting. Do you have any thoughts on how this generalizes to the case where the environment is only partially observable, where there's measurement error, and where, you talked about you not being able to guarantee that a value is satisfied because of other agents' actions, but what if you can't guarantee that a value is satisfied because of uncertainty about the environment?
Yeah. So I have given some thought to this. And it turns out you can still do a lot of the same reasoning. For example, if you want to be sort of really technical about it, you can just say, well, we assume that there is the environment is itself one of the agents, and it can take various actions that change the values of the unobservable propositions. So then all of the definitions still work. Because you just say, well, if the environment is fully observable, but we have these agents that act effectively randomly, then we just have to evaluate our responsibility over all of the possible plans that those agents could perform. If the environment itself is not observable and there's agents, then we have to evaluate over all possible combinations of all possible states of the environment given our observations and all possible plans of the other agents. And then all of the notions still work. You still have the notions of active and passive responsibility and so on. It does obviously get a lot harder because now there's more options to evaluate, and it's less likely that there's a plan that always works, but the definitions still hold up.
Thank you. Any other questions from Colin at the front, in the middle?
Thank you, Tim. How many of your results can you get, or how many of your operations can you replicate if you use existing legal terminology rather than new terms like active and passive responsibility? So I was thinking, for example, there's a concept of jointly and severally liable. How close is that to your concept of, what was it, passive responsibility?
Yeah.
And then I guess individually, because it seems to me that if you can do it in the existing legal language, then all of a sudden you've got this huge machinery that you can crank with.
Yeah. So a few things on that. So this comes from philosophical notions of responsibility. So it is also pre-existing, but in a different literature. Thing is with notions of legal responsibility is that they often, to be legally responsible for something often includes notions of knowledge. You know, what you could have reasonably expected to occur, things like this. And it's something we sort of like to be able to formalize, but I think it's quite a bit more complex than the notions we have here. I mean, I'm more familiar with notions of moral responsibility because my background is philosophy much more than law. And it's generally taken, for example, that causal responsibility, at least one of these notions here, is a necessary but not sufficient condition for moral responsibility. So formalizing this gets you part of the way to moral responsibility, but not all of it. And
okay, so to be provocative, for you to engage properly with legal machinery, you need to enrich this modeling structure to add, for example, knowledge operators or awareness operators. Okay. Because I think the moment you can do that, that becomes really powerful. Yes.
No, I mean, this model is sort of very bare bones. There's a lot of things that it would be nice if this model can do that it can't, because you know, walk before you can run, I guess. Build a simple model, understand what applies in that model, get a good handle on that, and then start making it more complicated.
No, that sketches out a very interesting research agenda, though.
Yes, I would agree.
I mean, there are legal systems that are automating at the simple, like parking ticket evaluation, for example. So there's a big project of trying to offload expensive judiciary costs. Thank you.
Can we run a mic to Manuel in the back corner?
Oh, thanks for the talk. So this is, I guess, quite speculative. I don't have, like, you know, anything particular in mind. Have you explored, like, different kinds of logic? Like, you know, different kinds of, I don't know, logical operators, different, I don't know. Have you thought about, like, you know, things that, you know, you might want to have at some point, or maybe things you didn't want to have, or, I don't know, very open-ended, kind of?
Yeah. That's a good question. So in terms of serious study, we've just looked at what's called linear temporal logic over finite traces. And the reason we use that particular logic is because we evaluate all our values over a history, which is primarily, well, just a sequence of states plus the actions. And that is exactly the model over which LTLF is designed to be evaluated. It is sort of provably the most general complete logic for that particular setting, so that's one we use. Obviously, for a lot of values that you would want to talk about, it's not sufficient. So, you know, particularly if you want to start writing values for something like ChatGPT, a lot of the values you're going to want to write will involve knowledge operators. You know, you don't want to make statements that will cause someone to gain certain knowledge or cause them to form a certain belief. So then you will need a more complicated model that includes belief and knowledge, and then correspondingly you'll need some sort of epistemic or possibly temporal epistemic logic that can talk about that sort of thing. So the idea with this, again, the LTLF is kind of just there as a placeholder, because these ideas, these definitions of responsibility and dilemmas, they are pretty much agnostic to which logic you're using. All I need to know is that you have a model and that you have a logic that can be evaluated over that model, and then all of these rest of these definitions follow. They don't depend really on any specific feature of the logic. The only thing it's nice to have is that the logic is binary valued, because if you start getting into multi-valued logic, then a lot of these definitions will need refining to account for that.
Was there a question from the back right corner? Question mark?
That too.
Hi, thanks for the talk. I was wondering, at the beginning you were saying sort of we would want verifiability, we'd want this kind of logical guarantee. I was just interested in the context of like modern systems which tend to be pretty good at kind of roughly getting the boundaries between various logical values. And then I guess philosophy's kind of historic difficulty with ever actually really nailing down where the boundary of a certain value should be. I wonder if you could say a bit more about when you think it's actually, we really would actually want to trust a logical system rather than a messy kind of intuitive system.
Yeah, for sure. I mean, you are correct to say that, as I say, one of the very large assumptions I've made is that we just have this translation of values into logic that we all agree is sufficient and accurate and correctly, cuts down the middle of all the ambiguity, which is a very unrealistic assumption in some ways. But I think exactly what kind of values you want and how much you trust them will depend a lot on the context that the agent in particular is operating in. I think in some contexts, you can express pretty much all the values you want in a very straightforward way, in a way that seems to be quite clear that these are the values you want to express. Because while I think this model is applicable to AI, it's also intended to be used even at much lower level kind of robotics type applications. So an example there is that in the current real world, you have warehouse robots that trundle around warehouses and move packages around. And from what I understand about reading into these robots, they have effectively one value, which is don't bump into things. And given that these robots have been trundling around warehouses for several years now, it seems we can be quite satisfied that that singular value is entirely sufficient. Yes, you can construct some theoretical sort of trolley problem type case where the brakes fail and it's got to choose who to run over, but in practice these things don't happen. So that would be one thing. The other one being that you don't necessarily have to have the logic-based system having complete autonomy over the some more, vague type system. You can have them all work together and try and exploit the strengths of each. So we can have something that says, only let it through if both of these agree that it's a good plan. So if both of them agree, if the logical system and the more vague intuitive system agree, then it's definitely a good plan. And if they disagree, again, call some other system, go ask a human, something like this. Yeah. Thanks.
We have time for one more.
Thank you. I guess you kind of answered this question a little bit. So I was thinking, because I think that for AI systems in the future, when they're more like agents and they have more agency and serving many people at once, the ontological systems of values will be insufficient, and you'll have something more like virtue-based, because you can operate on a few laws. There are so many unknowns, so you kind of have to operate on something more like that. So I'm curious about how you think this model could work on a sort of virtue definition of values, and if it would work at all.
Yeah, I have given less thought to how to interpret sort of virtue ethics type values. But I think at least some of them you could attempt to formalize, so a value of be honest. That one's relatively straightforward, particularly if you have an agent. Because if it's advanced enough that it needs virtue ethics type agents, I think we can also hopefully assume it's advanced enough that it has a pretty good understanding of things like people's beliefs and the likely effects of its actions on people's beliefs. So then it can do stuff like, you can just put the value in of, don't deliberately do actions that will knowingly cause false beliefs that you're using for an instrumental goal or something like this, right? Which is roughly a formalization of be honest. As for other things, I don't necessarily know if they would be virtue ethics type values, but you can just make values that are extremely broad. So, you know, avoid suffering in humans, something like this. Because again, if we're getting an agent that's so advanced that more specific values like don't collide with humans, don't burn humans are no longer sufficient, then hopefully it's also advanced enough that it can actually do the required reasoning to understand a more nuanced definition of what exactly is harm, particularly if it can, you know, understand human desires, it can predict human desires, then you can reasonably well just say, well, harm is anything that very strongly goes against a human's desires. Because we kind of all have desires not to be injured or burned or, you know, whatever. So, yeah, I think there is a lot of scope, particularly as the agent gets more advanced and therefore more intelligent and able to interpret a wider range of terms. There is scope to make values that those agents can continue to work with up to quite a high level. But this isn't something I've hugely analyzed, I have to admit.
Right, thank you.
Okay. I think that's all we have time for. Thank you, Tim.